Well, hello, everybody. I'm Bryce Adelstein Lelbach. So I started programming about a decade ago, actually working at Louisiana State University with Steve and Hartmut-Kaiser. And I've spent most of my time in HPC and working on programming languages and compilers. So I chair the standard C++ library evolution group, which designs and standardizes the C++ standard library. And I also chair the American Committee for Programming Language Standards. And I'm the editor for the Inclusive Terminology Guidelines and Standards for the Insight Standards body. So I work now at NVIDIA, where I lead our strategy for HPC programming models, C++ compilers, and C++ libraries. Before that, I worked at Lawrence Berkeley National Lab. And then before that, I was at Louisiana State University, as I mentioned, where I worked with Hartmut-Kaiser on the HPX parallel programming framework. So today I'm going to talk to you about the C++ committee's plans for bringing parallelism, asynchrony, and accelerated computing into standard C++. If my clicker works, that is. There we go. So the barrier for parallel programming today is far too high. We live in a world where almost all hardware platforms are parallel and require explicit programming to utilize that parallelism. And despite that, many users and many code bases do not utilize parallelism. And for those that do, many have chosen an approach for parallelism that's not portable to accelerators such as GPUs. And so because of that, the C++ committee wants to build an on-ramp to parallel programming. We want to give users easy to adopt solutions that are universally portable. We're not necessarily looking to expose all the capabilities of each platform or the absolute speed of light in every case for each platform. Instead, we want to provide something that's going to be able to be widely adopted and that will help normalize parallelism across the C++ ecosystem, and that will, of course, be portable. So there's three pillars to our strategy for parallelism in standard C++. First, we need a corpus of common algorithms that can dispatch to vendor-optimized parallel libraries. Second, we need tools to allow you to write your own generic parallel algorithms that can run anywhere. And then third, we need mechanisms for composing parallel invocations into task graphs. So essentially, we need mechanisms for asynchronous programming. So let's start off by talking about that first pillar, the collection of common parallel algorithms. So C++ has a set of serial algorithms for manipulating sequences of objects, and these have been there since the first C++ standard. These algorithms operate on one-dimensional sequences. Initially, these were parameterized with iterators, but with C++20, we've introduced a new, more powerful abstraction that builds on top of iterators called ranges. There's about 100 different standard C++ algorithms. We have for loop abstractions, filters, sorts, searches, rotations, reductions, scans, etc. And in C++17, we introduced parallel versions of these algorithms. So the parallel overloads have the same interface as their serial counterparts, except that they take an extra parameter, an execution policy, that describes what form of parallelism is allowed, if any. So execution policies describe the how of execution, but they don't specify the where. That's left up to the implementation. So execution policy parallelism could be implemented with a variety of strategies. It could be a bespoke CPU thread pool, it could be OpenMP, or it could be GPU acceleration. Execution policies permit parallelism, but they do not require it. So an implementation may choose to not parallelize or may choose to not parallelize every call in every situation. These execution policy overloads are all fork join synchronous. So the implementation will wait for the parallel operations to complete before returning from one of these algorithms. So there's 4 different execution policies in the standard. The seek policy indicates that all operations must be performed within the calling thread and must be indeterminately sequenced. So basically, it says no parallelism is allowed. The unseek policy also requires all operations to be performed in the calling thread, but allows those operations to be unsequenced with respect to each other, which means that vectorization is allowed, but not required. So par allows the implementation to parallelize operations at its discretion. It does not require parallelization. It simply allows it. However, it also requires that all the operations within each thread must be indeterminately sequenced, which means that vectorization is not allowed. And then finally, we have par unseq, which allows operations to occur in multiple threads and to be unsequenced with respect to each other, meaning that both thread and vector parallelism is permitted. So again, this means that parallelism and vectorization are allowed, but not required. An implementation may choose to not parallelize or vectorize, or may choose to not parallelize or not vectorize in certain situations. For example, if you're calling a parallel sort on two elements, a good implementation is probably not going to try to parallelize that. So now let me show you one of my favorite parallel algorithms examples, which is a parallel word count. So we're going to write this with a single parallel transform reduce. So transform reduce takes both a transformation operation and a reduction operation, and it applies the transformation to the inputs and then uses the reduction to sum the result of those transformations. So if you're familiar with MapReduce, this is C++'s version of it. So we're going to use the overload of transform reduce that takes two input sequences and a binary transform function. The first input sequence is going to be the entire string except the last element. And the second input sequence will be the entire string except the first element. And so this means that our binary transform function was going to be passed a window of every two adjacent characters in the string. So our transformation function's job is to tell us whether the two adjacent characters that we're looking at are the beginning of a word. And so if the left character is white space and the right character is not white space, then the right character is the beginning of a word. So the pseudo sequence that's going to be produced by the transformation is going to look like this. For every word, one and only one of the transformation invocations is going to return true. But what about the first character of the string? We never actually test it with our transformation function because we start at that second character. And so we need to account for that in the initial value of our reduction to make sure that we would count that first word. So our reduction operator is just plus. After the transformation, we're going to have a sequence of bools, and summing that sequence into an integer will give us the word count. So this is a standard C++ code. It's parallel and portable. You can run it anywhere. You can run it on your GPU. You can run it on your server CPU, on your laptop, even your phone or your watch. So in C++20, the C++ standard library introduced ranges. Unlike iterators, ranges are composable. Ranges allow us to express a wide range of algorithms in terms of a few key primitives. Used in conjunction, the C++20 ranges and the C++17 parallel algorithms can be quite powerful. So standard C++ algorithms iterate over sequences of objects, for example, the elements of a container. However, sometimes we want to iterate through indices instead of objects, and this is particularly important in numerical and scientific computing. We can do this using IOTA, a range factory introduced in C++20. So it produces a range of monotonically increasing integers. For example, IOTA 1n will produce a range of all integers from 1 to n-1. And this is done lazily, so it doesn't actually create any storage for these. They're just produced on the fly. So instead of passing iterators to a container to a parallel for each, we can instead pass an IOTA range, giving us a parallel for over the indices instead of the objects. We can also use parallel algorithms and ranges to iterate multidimensional index spaces. So C++23's Cartesian product range adapter takes multiple input ranges and produces a range of all the ordered tuples formed by taking an element from each of the inputs. So we can use this in conjunction with IOTA to create ranges representing multidimensional index spaces. So for example, here we're using this pattern to write a simple parallel matrix transpose. So the range V here will produce two element tuples from 0, 0 to n-1, m-1. The iteration order here will be row major, so the second index will be contiguous. And we can change to column major by switching the order of arguments to Cartesian product. So as I mentioned before, the C++17 execution policy parallel algorithms are fork join synchronous. So each invocation launches its work in isolation and blocks until that work completes. So for example, if we invoke two parallel for eaches on the same data back to back, we'll get two parallel work launches. The caller will be blocked, waiting for the first invocation to finish, and only then will the second invocation be queued and launched. This transfer of control back to the caller is a latency bubble, and it can degrade performance, especially on platforms where you may have a higher latency to your compute resource, like a GPU. So one way to address this problem is to fuse operations together into a single parallel invocation, which can be done with the transform range adapter. So transform takes an input range and a function and returns a range that is the result of applying the function to the input. And this is completely lazy, so the function is only evaluated as needed when the elements of the returned range are accessed. So for example, here, f is not evaluated until the elements of v are accessed in the parallel for each. Now, this is a big change in semantics because previously we had a guarantee that all invocations of f would happen before any invocations of g. And so we no longer have such a barrier here. But in some cases, that might be perfectly fine for you. So another useful range adapter is filter, which takes an input range and a predicate function and produces a range of all the elements for which the predicate returned true. So again, this is done lazily. The predicate isn't evaluated until the elements of the returned range are accessed. So here we use filter in combination with a parallel reduction to sum only the positive elements of a container. So now let me show you some applications and mini apps that have adopted standard C++ parallelism. So Lelbach is a mini app for Lagrangian explicit hydrodynamics on an unstructured grid. It's designed to stress vectorization, parallel overheads, and on-node parallelism. It's been ported to several frameworks and programming models, including MPI, OpenMP, OpenACC, CUDA, Raja, Cocos, and now standard C++. With the standard C++ version of Lelbach, you can get performance that matches many of the other backends, and you can build that same standard C++ code with multiple compilers, GCC, NVCC, NVC++, the Intel compiler, and the Microsoft compiler, and run this code in parallel on either CPUs or GPUs across a wide variety of platforms. Another example is STLBM, which is a lattice Boltzmann framework that was written from the ground up in standard C++. So it can run on multi-core CPUs and GPUs without any code changes. And it doesn't use any language extensions, external libraries, vendor-specific code annotations, or pre-compilation steps. It's just purely standard C++, and so it's completely portable. So another example, Maya, which is a code base for aerospace flow and noise simulations, has ported to C++ standard parallelism, and they're planning on replacing their OpenMP backend with standard C++. And so the same standard C++ backend that they have can run in parallel on the CPU or run in parallel on the GPU. So these C++ 17 parallel algorithms are great, but they're really just the start of the story. They have two major limitations. So first, they are all fork join synchronous. So they launch the parallel work, and then they wait until that work has completed before they return to the caller, which, as I mentioned earlier, creates this latency bubble that's undesirable. Now, where exactly do they launch that work? And that's the second problem. By design, users have no control or visibility into where the parallel work runs. It happens on some amorphous implementation defined execution context that could be a CPU thread pool, it could be a GPU stream, Grand Central Dispatch, Windows Fibers, etc. Implementations have complete freedom and users have essentially no control. So today, C++ has no standard model for asynchrony and has no standard way to express where things should execute. But the solution is coming soon to your C++ implementation. And that solution is senders and receivers, which is an asynchronous execution framework for standard C++. So let's look at a simple example. So first, we need to get a scheduler from somewhere, from a thread pool, a tasking system, a GPU driver, etc. And then to start a chain of work on that scheduler, we call schedule, which returns a sender. And that sender will complete on the execution context associated with the scheduler. Next, we're going to use a sender algorithm then to compose onto the sender that we just got from the scheduler. And this work will be performed on that same execution context. The sender algorithm will return a new sender, which we can use to add more work onto that chain. And then finally, we wait until the chain of work has completed using sync wait, which will return the value sent by the final sender in the chain. There are three key concepts in this model: schedulers, senders, and receivers. So schedulers are handles to execution contexts, and they produce senders. So they describe a location or a mechanism or a strategy for scheduling work on some concrete execution context. Senders represent asynchronous work that will be sent eventually, that will eventually send some signal. And they can be composed together with sender algorithms to form task graphs. Now, receivers process the asynchronous signals that are sent by senders. So let's look at schedulers in a little bit more detail first. So I said that they are handles to execution contexts, but what exactly does that mean? So an execution context is a resource that represents the place where execution will happen. So this could be a concrete resource like a specific CPU thread pool or a GPU stream. It could also be a more abstract resource like the current thread of execution. Execution contexts don't necessarily have representation in code, and today they don't have any exposed interface. They may have state associated with them like OS handles, memory, metadata, etc. Schedulers represent a strategy for submitting work to an execution context or multiple execution contexts. They are lightweight, non-owning handles to the contexts, and so thus schedulers are cheap to construct and pass around. The execution contexts themselves hold all the state. Multiple schedulers may refer to the same execution contexts, including multiple different kinds of schedulers. For example, you might have two schedulers that submit work with a different priority to the same execution context. You might even have a scheduler that dispatches work to multiple different execution contexts. For example, a scheduler that distributes work across a CPU and a GPU. So we use schedulers to produce senders that will perform work on the execution context associated with the scheduler. Once we've obtained a sender from a scheduler, we can compose work on it. So now let's take a look at senders themselves and how we actually compose them together. So as I said before, senders represent asynchronous work that will eventually complete and send some signal. They form the nodes of an asynchronous task graph, which may span multiple schedulers and multiple execution contexts. Senders are lazy. You must explicitly start them. And when a sender's work completes, it sends a signal to the receivers that are attached to it. So receivers are handlers that get notified with a signal by a sender. And there's three different handling paths, which are called channels. The value channel is used to indicate successful completion and may pass one or more values to the receiver. The error channel indicates that the sender's work failed and passes an error object that contains information about that failure. The done channel is used to indicate that the sender's work was canceled before it could be performed. And this is distinct from the error channel because cancellation is not an error. It's something that may happen during the course of normal operations. So each sender will notify its attached receivers with one signal, meaning only one of these three channels will be invoked. So now let's take a look at how senders and receivers are hooked up to each other. So we're going to start off with some scheduler, which we will get a sender from. A receiver is going to be attached to that sender via connect. This is a behind-the-scenes interface that won't usually appear when you use asynchronous operations, but you might see it if you're implementing your own asynchronous operations. So connect returns an operation state, which contains the actual work that the sender represents. Eventually, you initiate the work by calling start on the operation state. And after some time, the operation completes, and then it notifies the receiver with the signal. So now let's take a look at sender composition. So we compose together senders using sender algorithms, of which there are a few forms. The first is sender adapters. So sender adapters take one or more senders as parameters, and they return a sender. Most sender adapters are pipeable, just like range adapters. So the semantics here are similar to Unix shells. Send pipe F pipe G is equivalent to G of F of send. So languages like Haskell and APL call this point-free style. The primary input argument is not explicitly named. And this syntax is essential for the elegant composition of senders. Composing senders via nested function calls would be a bit of a mess. The order in which operations occur is inverted from the order in which they appear in code. The predecessor senders are more deeply nested and thus appear after their ancestors. Things get a bit clearer when we instead use a temporary variable for each stage of the composition. But this is pretty error prone because it's easy to mix up one of these named variables. The pipe syntax gives us a clean way to compose chains of senders in the order that they will be evaluated. So now let me show you some of the most important of the sender adapters. So we've already seen one of them, then, which takes an invocable F and calls it with the values sent by the prior sender. The sender returned from then will send the results of that invocation of F. So this is how you attach a continuation to a sender. Bulk is quite similar to then. It evaluates the invocable once for every index in the shape n. In the simplest and most common case, the indices are one-dimensional and start at 0, and the shape argument is just an integer indicating how many invocations to perform. The sender that's returned from bulk will pass along the signal from the prior sender. Now, transfer changes the scheduler that will be used for the next sender, but it doesn't change the scheduler that's going to be used for any of the prior senders. Some senders can only be connected to a single receiver, for example, because they move any values or errors that they send instead of copying them. We call these one-shot senders. Senders that can be connected multiple times are called multi-shot senders. So split is an algorithm that takes any type of sender and returns a multi-shot sender that passes along the signal from the original sender. So split senders represent forks in a sender task graph, or parallelism. Conversely, WinAll takes multiple input senders and returns a single aggregate sender that will send the signals from all of the inputs. The senders returned by WinAll do not have any scheduler associated with them, which means they do not promise where they complete. So WinAll senders represent the joins in a sender task graph. Ensure started connects and starts a sender, returning a new sender that will pass the signal sent by the original. As I mentioned earlier, senders are lazy. And so if you want to start them eagerly, you need to use something like ensure started to kick off the part of the task graph before you've finished building it. If the input sender is a composition that's containing other senders, then those senders will be connected and started as well. So sender factories are another kind of sender algorithm. They do not take senders as parameters, but they do return a sender. So sender factories are used to start new chains and graphs. The senders that they return are the root nodes. We've already seen one sender factory schedule, which returns a sender that completes on the specified scheduler. The return sender doesn't send values or represent any actual work. It's just a handle that you can use to compose work on the scheduler. Just is another sender factory. It takes a set of values and produces a sender that will send those values immediately when connected. So it's a way to introduce outside values that are already available into a sender graph. So the last kind of sender algorithms are sender consumers. They take senders, but they do not return senders. So they typically launch a sender graph by connecting and starting it. So these are the leaf nodes of sender graphs. So sync wait is a sender consumer and synchronization primitive that will block until a sender completes and then return or throw whatever was sent. So now let's discuss the details of how these sender graphs get formed. So let's suppose that we have a single link in a chain of senders. So we're going to have an abstract before sender adapter on the left-hand side of this link, a concrete then adapter that's applying some function f, and then a abstract after adapter on the right-hand side. So if we unroll this pipe syntax, we'll have something like this. We've got a before sender that came from somewhere, and we create a then sender, which will contain the before sender and the function f. And we'll also create an after sender, which will contain the then sender. So we're going to end up with a nested structure of senders that sort of looks like this. And at some point, we'll connect a receiver to the outermost and last sender. Each sender in the nested structure will connect a receiver to its child, and this will happen in the opposite order of sender construction. You sort of go down the graph, and then you go back up when you connect the receivers. And this will give us a nested receiver structure. That's the inverse of the sender structure. And also a nested operation state structure is produced and returned from the call to connect. Eventually, we'll start that operation state. And as the operation's complete, they'll begin notifying their receivers with signals. When the before receiver gets its signal, it will notify the then receiver. If it's a value signal, the then receiver will invoke f with that value and signal the after receiver with the result of that invocation. So let's look at a slightly more advanced example. We're going to write a generic asynchronous and parallel inclusive scan. And we'll write it as a pipeable sender adapter so that it can be composed with other sender algorithms. It'll take 3 parameters: a sender, which we'll expect to send the input as a range, an initial value, and the number of tiles to split the input into. So we're going to use the classic 2-pass parallel scan technique, which requires temporary storage for partial results communicated between tiles. We need to allocate this temporary storage asynchronously once the prior sender has sent us the input. So we'll chain a then sender onto the prior sender. And in the body of the continuation, we'll create a std vector to hold the partials result. We'll return both the input range and this temporary vector, which we want to pass on to the next thing in the chain. Next, we need to do the first parallel pass, the downsweep. So we'll use bulk to invoke the body of the pass for each of the tiles. The first thing we do for each tile is calculate the range of elements that belong to that tile. Then we take all of the elements in each tile, and we perform a local serial inclusive scan on them, which we do right here in the code. Next, we need to propagate information between the tiles. So the sum of each tile needs to be added to the elements of all preceding tiles. We've already computed that sum. It's the last element of the local inclusive scan. So we store that result into the partials vector. So assignments to partials from different tiles will happen concurrently, but that's fine because each tile uses a different and unique slot in partials, and no one reads from partials yet, so there's no data race here. Then after all the tiles have completed their local inclusive scans and written to partials, we need to have one execution agent do a serial inclusive scan of that partials vector. And we're going to do this by piping another then sender onto the chain, which will perform the partials inclusive scan. This then sender will again pass along the input sequence and the partials vector. So the result of the scan over partials looks like this. The information that each tile needs to add to its elements is in the partials slot for the tile directly preceding it. And now we need to go parallel again to distribute this information within all tiles. This is the upsweep pass. So we'll pipe another bulk once again over all tiles. So in the body of this bulk, we need to calculate which elements belong to the current tile, just as we did before in the downsweep pass. And then we use a serial for each to increment each element in the tile by the appropriate value from the partials vector. And so after that addition, we'll have the correct result in each output element. Finally, we want the sender returned by our asynchronous inclusive scan to only send the input sequence, not the partials vector. And we want to destroy the partials vector at this point because we no longer need that temporary storage. So we add a final then sender, which only passes along the input. And the partials vector will be destroyed when this then sender completes because it'll go out of scope. And so that's it. We're done. We've got a generic, asynchronous, and parallel inclusive scan. And we can run this on any scheduler that we want, which means we can run it on a CPU in parallel, on a GPU in parallel. We could run it in distributed. We could run it on a single thread just by changing the scheduler that we plug in here. So we can imagine that we'll have a whole set of asynchronous parallel algorithms based on senders and ranges. The design space for these interfaces is still open. It's straightforward for some common cases, like a series of for eaches over the same sequence. We could have an in-place transform async, which takes a sender of a range and a callable and returns a sender of a range. And then it becomes easy to rewrite that series of synchronous for loops into a lazy asynchronous operation using this transform async and the pipe syntax. So let's look at a slightly more interesting case, normalizing the elements of a range. Now we can do this by getting the maximum element of the range and then dividing each element by that one. It's a bit more challenging to map this to asynchronous execution. The piping syntax is great when you have one dependent value that you want to pass down the chain, such as a single input sequence. But in this case, there are two asynchronous inputs to the second call, the input sequence and the maximum element. So we may want asynchronous parallel algorithms to return richer senders. For example, reductions like max element async should probably send both the input sequence that was passed to it and the iterator to the maximum element. So as I said, this is a bit of an open design space. We're still trying to figure out what exactly asynchronous parallel algorithms will look like and what the composition syntax will look like for these asynchronous primitives. So we've developed a prototype implementation of standard C++ senders and receivers that supports CPU schedulers, GPU schedulers, and distributed schedulers. So let me show you some examples of the applications that we've ported to using it. So this is a simple electromagnetic wave simulation that solves Maxwell's equations on a uniform grid. So this is the entire solver loop, which is expressed as a graph of senders. So this code can be run with a variety of different schedulers. By changing just one line of code, the kind of scheduler passed to the solver, we can go from running inline on a single CPU thread to running in parallel on the CPU using OpenMP, to running on a single GPU, to multiple GPUs within a single node, to multiple nodes scaling up to thousands of GPUs. So with standard C++ senders and receivers, you can change one line of code and scale from a single CPU thread up to an entire cluster of GPUs. So Palabos is another application that we want to highlight. It's a framework for parallel computational fluid dynamic simulations using the lattice-Boltzmann method. And we've ported one of its applications to standard C++ senders and receivers. So this simulation models carbon sequestration techniques. So the porous structure that you see is sandstone, and it's filled with saturated salt water, which is not visible on this representation. The red bubbles correspond to liquid CO2, which is injected at the bottom and travels up through the sandstone because of buoyancy forces. So using our distributed GPU scheduler, we've been able to run this application at scale on up to 512 GPUs. So senders and receivers are the next major step in the development of C++ standard parallelism. They deliver the second and third pillar of our plan. The framework gives us the tools we need to write our own generic parallel algorithms that can run anywhere and compose asynchronous task graphs. So following the standardization of senders and receivers, we'll introduce new asynchronous sender-based versions of the standard parallel algorithms. Now I want to shift focus a little bit and talk about new families of algorithms that are currently missing from the C++ standard and the tools that we need to be able to write these algorithms, specifically multidimensional algorithms. So today, C++ has no reasonable abstraction for multidimensional data. And this is unfortunate because many of the interesting compute-heavy problems that benefit from parallelism have a multidimensional shape. And that's why we've introduced MDSpan, a multidimensional span type in C++ 23. It's very similar to the one-dimensional span that was introduced in C++ 20. So MDSpan is non-owning. It's just a handle to some underlying data. It doesn't manage the lifetime of that data. And thus, MDSpans are cheap to copy. It just contains a pointer and the metadata describing the size and shape of the structure. The metadata, such as extents of a dimension, can be expressed either at runtime or compile time, allowing for metaprogramming and compile time optimizations. MDSpan parameterizes how a multidimensional index is mapped to a location in the underlying data. We call this parameter a layout, and it expresses any kind of multidimensional structure. There are some concrete layouts in the standard library for common use cases, but anyone can define their own layout and plug it into an MDSpan. Likewise, MDSpan parameterizes how it accesses the underlying data. The default is just to perform a normal C++ pointer dereference with an index. But with a custom accessor, you could instead use a special cache bypassing instruction, read from disk, or perform a remote memory access. So MDSpan uses extents objects to express the number of dimensions in the space, the rank, and their length, the extents. So extents objects takes a size type and a variadic number of integrals of that type as template parameters. For dynamically sized extents, the magic value dynamic extent is used as an integral template parameter, and the extent is passed to the constructor. Through the power of C++ 20's class template argument deduction, when you're working with all dynamic extents, you usually don't need to spell out the entire verbose instantiation. There's also an alias dextents for the all dynamic extents case. It takes a single parameter and integral specifying the rank. For statically sized extents, the extent itself is passed as an integral template argument, and no corresponding constructor argument is needed. You can mix static and dynamic extents. For example, in this case, we have one static extent and one dynamic extent. So we'll need to pass just one extent at runtime to the constructor. Extents objects and MDSpan support arbitrary rank. You can have as many dimensions as you want. However, the rank has to be known statically. So MDSpan itself has 4 template parameters, 2 of which are optional. The first is the element type. The second is the extents type. And this must be a specialization of the extents class template that we just saw. The third is a layout, and the default is layout right, and we'll discuss layouts a bit more in a few minutes. And the final parameter is an accessor, which performs element access. So MDSpans of all dynamic extents have a pretty simple syntax. With class template argument deduction, you can construct one without specifying any template parameters. And if you do need to spell the type out, it's still pretty concise. You can just use the dextents alias. The elements of an MDSpan are accessed via the index operator. Thanks to a recent core language change in C++ 23, indexing operators can now take multiple parameters. So that's what we use as the overloaded indexing operator. You can also make MDSpans of static or mixed extents. The simplest way to construct these is by passing an extents object as the second constructor argument. So now let's talk a little bit more about layouts themselves. So the 2 most common layouts are layout right and layout left. With layout right, the rightmost extent is contiguous, meaning that its stride is 1 and the strides increase from right to left as a product of extents. So this is the layout for C++ built-in arrays and also for NumPy, and it's the default for MDSpan. For example, if we had a 2x2 matrix, the 2 elements on the first row would have data locations 0 and 1, and the elements on the second row would have data locations 2 and 3. With layout left, the leftmost extent is contiguous. Its stride is 1, and strides increase left to right as the product of extents. So this is the layout that's used by Fortran arrays and also by MATLAB. So if we had a 2x2 matrix in layout left, the 2 elements in the first column would have data locations 0 and 1, And the 2 elements in the second column would have data location 2 and 3. There's also a standard layout that allows you to explicitly specify the strides for each extent, and that's called layout stride. So all 3 of the concrete layouts in the standard library are just implementations of the layout concept. Generically, a layout is just something that maps a multidimensional index to a data location. Anyone can define a layout. They may be non-contiguous. They may map multiple indices to the same location. They may perform complicated or expensive computations, and they may have or refer to state. Parameterizing layout is critical because it allows us to write generic multidimensional algorithms that can be used with any layout. And this is an essential component of portability because different layouts may be needed on different platforms to deliver on performance. Today, we have a major vocabulary problem with multidimensional types in the C++ ecosystem. So suppose that I write a function that uses a concrete owning multidimensional type like eigenmatrix. My users will be able to pass an eigenmatrix to this function. But what if they have a boost ublas matrix or a PET-C matrix or a Blaze matrix or a Cutlass tensor or some multidimensional array that's been passed to them from Fortran? They're not going to be able to pass this into my function because my function expects an eigenmatrix. And that's where MDSpan comes in. By using it in your interfaces, your code can work with any multidimensional data structure. Because MDSpan is just a non-owning handle, you can construct one that refers to an eigenmatrix, to a boost ublas matrix, to a PET-C matrix, et cetera, et cetera. So for example, suppose that we had our own row major matrix class. We can add a simple MDSpan conversion operator, allowing us to pass our matrix class to any interfaces that expect an MDSpan. In some more complex cases, we might have to write our own layout type. But in a lot of the common cases, we can just use one of the built-in layout types. So now let's look at some examples of how we can use MDSpan. So this is a simple 3D 7-point stencil interkernel, similar to what you'd see in a proxy application like MiniGhost. We have 2 3D MDSpans representing the problem state. And using that Cartesian products of iota technique that I showed you earlier, we build a range that iterates the index space. And then we use a parallel for each to iterate through that space. And then inside of that parallel for each callback, our function object, we apply the stencil itself. And if we want to change the layout, all we have to do is change the input MDSpans. Everything else remains the same. So earlier I showed you this example of a simple parallel matrix transpose, and we used span and dealt with the multidimensional indexing manually. So that's not particularly portable. We've hard-coded a specific data layout, which may not make sense in all circumstances. And it's also error-prone, as it's pretty easy to make a mistake in the indexing formula. So we can improve this by using MDSpan instead. Now we can change the layout by simply changing the type of MDSpan that we use. Now, I'm fairly happy with that last slide, but I want more down the road. I'd like to be able to write something like this. And there's 3 things here that we don't have yet. The first is parallel algorithm overloads that accept ranges directly instead of iterator pairs, but that's coming down the road. And the second is some sort of indices method on MDSpan that returns a range of its multidimensional index spaces. If you're interested in learning more about that, I've given a whole separate talk just on that topic. Which you can find a video of online if you search for multidimensional C++ CPP North. And then the third is a language extension to allow us to destructure tuples and parameters, which is just kind of a nitpick, but it makes this code a little bit cleaner. And going even a step even further, we of course eventually want an asynchronous version of this that parameterizes where it runs on some scheduler, so that you can just plug in, a CPU scheduler or a GPU scheduler and have this run wherever you want. So MDSpan has a powerful slicing interface, sub-MDSpan. It takes an MDSpan and returns a sliced MDSpan. Because MDSpan is non-owning and cheap to copy, slicing is also cheap. You're just creating a new view of the same underlying data. The input MDSpan is not modified. So for each extent of the MDSpan, you pass a slice specifier to sub-MDSpan. And there are 3 types of slice specifiers. You can specify a single index to be selected for an extent by passing an integral as a slice specifier. And the rank of the returned MD span is reduced by 1 for each single index slice specifier, because you're slicing away that entire dimension. You can also pass a range of contiguous indices to be selected for an extent. And then finally, you can pass the special value full extent to select an entire extent. So for example, here we have a 3D MD span M0, and we make a slice of it by selecting 8 indices for each extent, starting at indices 15, 31, and 7, respectively. The MD span returned by sub-MD span M1 will have a rank of 3 because we didn't use any single index slice specifiers that would have caused a rank reduction. And each of the extents of M1 will be 8. The multidimensional indices for M1 will just be offset from what they would be for M0. So for example, M1 000 would be equal to M0 15, 31, 7. Let's look at another example, this time with rank reduction. So again, we'll slice M1, selecting index 15 for the first extent, the entire second extent, and index 31 for the third extent. So the MD span that we produce, M2, will have rank 1. And the extent of that rank will be 128, the extent of the second dimension of M0. So iterating this 1D slice will be equivalent to accessing M0 with a fixed index for the first and third extent. So sub-MD span is a useful tool for writing tiled algorithms. So let's build a tiled version of the parallel matrix transpose that we looked at earlier. And we'll work with square tiles with extent t by t. So first, we need a range describing the set of all tiles. And we're going to, again, use that Cartesian product of iotas trick for this. And it's OK if the tiles at the edges extend beyond the bounds of the matrices, because we're going to handle that in a minute. Then we're going to have our parallel for each. And this time, it's going to iterate over tiles, not all of the indices. And for each tile, we're going to create new sliced MD spans A and B using sub-MD span. First, we need to determine what range of indices we need to select based on the coordinates of the tile. And this is where we handle tiles that would go beyond the bounds of the matrices. We just truncate them to the ends of the matrices. And now we'll pass the tuples describing the indices we want to sub-MD span, producing the local MD spans for this tile. Next, we need a range of multidimensional indices within the tile. And then finally, we use a C++ range-based for loop to iterate over the indices of the tile and perform the transpose with the local MD span slices that we made. And with that, we're done. So the set of standard C++ algorithms that we have today is great, but it's not complete. What we have today is primarily focused on manipulating one-dimensional sequences of objects. We only have a very limited set of numerical algorithms, such as reductions and scans. And we don't want C++ programmers writing their own versions of common numerical algorithms like linear algebra primitives or FFT primitives. We want them to use standard interfaces that are backed by an implementation that's designed and optimized for the platform that they are running on. And so the C++ committee is exploring new families of algorithms to standardize, starting with linear algebra. So the C++ committee doesn't want to reinvent numerical linear algebra. We want to standardize existing practice, and the existing practice for linear algebra is, of course, BLAS, the basic linear algebra subprograms. But using BLAS libraries today from C++ is quite painful. They often have low-level C interfaces, which have a great number of parameters that describe things like extents, scaling factors, whether or not to transpose the inputs, et cetera. There's, half a dozen Boolean flags, and you have to know that this Boolean flag in this position means that, and this Boolean flag in this position means that. And depending on the platform that you're on, you may also have to deal with things like setting up library handles, transferring memory, et cetera. If you're using a Fortran BLAS implementation, you may have to use one of these little wrapping headers that make sure that the symbols are available. And so what we want to do is we want to standardize a modern C++ interface that can be implemented under the hood by these existing BLAS libraries, but does not look as painful to use as these are. And so here's that same code written using the new C++ standard linear algebra algorithms. So the existing one-dimensional C++ algorithms parameterize data with iterators and since C++20 ranges. For standard C++ linear algebra algorithms, we plan to parameterize data with MD spans instead. We use the MD-span parameters to express things that appear as distinct parameters in traditional C-style BLAS interfaces. For example, instead of having scaling parameters on matrix vector product, we have a scaled operation that takes a scaling factor in an MD-span and returns a new MD-span that will apply the scaling factor upon access. Now, C++ standard library implementations can see through this abstraction and extract the scaling factor to feed it to a lower level BLAS interface that expects it. Another example is transposed, which returns a transposed version of the supplied MD-span. And as with today's C++ algorithms, we're planning to have serial and fork-joined parallel overloads of the linear algebra algorithms. In this example, we're solving a system via upper triangular Cholesky factorization. And we'd really want to chain these two operations together and launch them asynchronously. So we imagine that down the road, we'll have asynchronous sender adapter forms of these algorithms that will allow you to do just that. So there's plenty of other work down the road for C++ standard parallelism. There's other classes of numerical algorithms to standardize, like perhaps FFTs. There's asynchronous streams, memory model extensions to support distributed computing, affinity and locality facilities, etc. But with every standard revision, we're delivering more and more components of C++'s story for parallelism. So I want to end where we started with our goal. And our goal is that we need on-ramps to parallelism in standard C++. Almost all modern platforms are parallel, yet a shocking amount of code does not take advantage of that parallelism or does not take advantage of all forms of parallelism, including accelerated computing. And so what we want to do is we want to normalize parallelism and accelerated computing. Writing parallel C++ code should be easy and natural, and parallelism should be the default, not something that you're opting into. So thank you all for your time, and if we have time, I'll take a few questions. But
we do have time.
Yeah.